Okay, so thank you for the introduction, and I'd like to thank the organizers for the invitation. So let's first briefly see the outline for my mini course. So I will spend some time on the Braverman-Kazhdan-Ngo and the Tamagawa theory, including local theory and the global theory. And then I will spend some time on the proposal of Braverman-Kazhdan and some detailed refinement by the Ngo. Okay, let's start. So let's first see the local theory of Braverman-Kazhdan-Ngo and Tamagawa. So let's fix our group G to be GLN. And we fix a local field F. For convenience, we assume that the local field is a p-adic field. There are parallel results for the Archimedean local field and function field, but for convenience, we restrict ourselves to the p-adic field case. Our goal here is try to establish the analytical theory of the standard L functions for GLN. Using the integral representation of L functions. There are two main ingredients in the local theory. One is the Schwarz space, and the other is the Fourier transform acting on the Schwarz space. So let's first talk about the Schwarz space. Since our group G is GLN, we have a natural embedding from G to Mn, the space of n times n matrix. Here, I would like to mention that actually this is a. What do you mean by in what sense? Yeah, it's a good point. Here I would like to mention that it's a G cross G equivariant embedding. Here the G cross G action on G and Mn are just by left and right translations. And for those of you who are familiar with the theory of spherical varieties, I would like to say that it's actually an affine spherical embedding. And as mentioned in Lei's talk, we know that Mn is actually a reductive monoid. And in particular, it is the only smooth reductive monoid up to finitely many copies. Then, what is the Schwarz space? We consider the space of locally constant and compactly supported functions on Mn. And then we do restriction to G. Then this is the Schwarz space for the standard representation of the dual group of G. Restriction. Okay. Then let's consider the Schwarz space, the Fourier transform here. Since we know that Mn is a vector space, so there's a natural Fourier transform acting on the Schwarz space. Defined as follows. For any test function f lies in the Schwarz space, we let fx just to be the integral transform given by psi of trace xy times fy dy plus. Here, dy plus is a fixed Haar measure. On Mn. And the psi is the additive character of the underlying field. And that is self-dual. And yeah, it's self-dual with respect to dy plus. In other words, if you apply the Fourier transform twice, then you get f of minus x. Okay. Here, sometimes we abuse the notation. We just let f check to be the Fourier transform. Now we are ready to talk about the main series in the local series of Goldman, Jacquet, and Tamagawa. So let me use this one. So any questions on the two main ingredients? Which part? Oh, you are right. Actually, this one also works, actually. You can verify that. Yeah. So any other questions? Okay, then let's talk about the main theory. So, yes, it's a good point. Yeah, let me make a remark here. The Fourier transform stabilizes the Schwarz space in particular. Actually, the transform is just defined on the monoid, so yeah, let's talk about the main theorem. We fix a smooth, irreducible admissible representation pi of G, and we can consider a space of matrix coefficient for pi. Then let's form the following family of distributions on the test function space, parameterized by complex numbers. Here, f is a test function, and the phi is a fixed matrix coefficient. Then the following theorem is proved. There are the following facts. The first fact is that the integration defined here is absolutely convergent whenever the real part is sufficiently large. The second fact is the meromorphic continuation and the Gcd property for the distribution here. So in the p-additive, since we are working with the p-additive field case, then the theta integral here is actually a rational function in Q to the minus S. Here Q is the cardinality of the residual field of F. And the following set, I pi, which is defined to be all such theta integrals. Admits greatest common divisor, which we call the L factor. And it's independent of the function and the matrix coefficient that you choose. And third fact is the functional equation associated to the distribution. Yeah, this is, the property here is usually called the Gcd property. Let me write here. The greatest common divisor. The third fact is the functional equation. So you can show that there exists some rational function lies in the fraction field in one variable Q to the minus S, such that the following identity holds. Here, phi check G is just phi G inverse. In particular, it is the matrix coefficient of the smooth conjugate of pi. Okay, so these are the main statements in the local theory of Goodman-Jacquet and Tamagawa. It's a central, let me briefly mention, if I remember correctly, then if you replace F by a division algebra over F, then that case is treated by Tamagawa. Yeah. So any questions on the main statement here? Yeah, GL over D, GL over D, just D cross, I mean, yeah. Okay. He's represented, he's a character. Yeah, just character, yeah. Your Iwasawa series, the GL1 case, yeah, of course, yeah. Let's first see how to define the standard L factor if we assume the theorem here. So if we're assuming the main theorem, let's see how can we define the standard L factor. So for any test function f, and the matrix coefficient phi, when you fix the element h in G, we let the right translation of f and phi by f1 and phi1. So we let f1 G to be f of gh, and phi1 of G to be phi of gh. Then let's form the zeta integral associated to f1 and phi1. Okay. Then, if we do change of variable, we find that it's equal to determinant of h to the minus s minus n minus 1 over 2. And the original zeta integral associated to f and phi. Yeah, let's see. So in particular, the set I pi here, we find that it's actually a fractional idea. Let me first write as follows. It is C of q to the s, q to the minus s modulo in the field of Lorentz polynomials. So in particular, it's a fractional idea. On the other hand, let's fix a non-zero matrix coefficient phi, which is non-zero, and we assume that phi evaluated at the identity point is non-zero. Since the matrix coefficient for PID representations are always k-finite, so you can find some open compact subgroup k0 such that it fixes the matrix coefficient phi here. Then if you run the zeta integral associated to the characteristic function of k0, the phi here, then you find that it's actually a constant. It's just a constant. So in particular, you find that the set I pi contains all the regular functions in variable q to the s and q to the minus s. So then we use the fact that this ring is actually a PID. Then we know that the fractional idea should be of the following form. So in particular, the fractional idea I pi here has a generator of the following form. P of q to the minus s, here p and the inverse, and px is a regular function. And you can normalize the polynomial here such that the value at 0 is equal to 1. Then we just define Ls pi to be p of q to the minus s to the minus 1. Yeah. This is how we define the standard L factor. On the other hand, we find that since the set I pi is non-zero, as we have already seen here, then from the functional equation here, we know that if the gamma factor exists, then it must be unique. So the gamma factor, gamma s pi per psi, is unique in particular. From the gamma factor, we can define the epsilon constant as follows. Yes, this is, yeah. Yeah, yes, you just mentioned, let me briefly make a remark here that under the local length correspondence, the L function defined by Goldman-Jack K is equal to the, defined by Goldman-Jack K is equal to the L function, Artin L function associated to the weight Zhilin representation. Yeah, anyway, yeah. Okay, let's see. Then we define the epsilon constant as follows. We let the epsilon constant to be gamma of S pi psi times L S pi over L1 minus S pi check. Then the functional equation becomes the following expression. The left-hand side of the original functional equation over L of 1 minus S pi check is equal to epsilon constant times the zeta integral over original zeta integral over L S pi. Then in particular, we find that the since we know that L zeta of S F phi over L S pi belongs to the ring of regular functions in variable q to the s and q to the minus s. So in particular, we find that the epsilon constant is a unit in the ring of regular functions in q to the s and q to the minus s. Since both epsilon constant and its inverse lies in the ring here. So in particular, it's always a monomial in q to the minus s. Okay. So finally, let's briefly mention the functional equation associated to the gamma factor. Let me erase here. A brief corollary from the functional equation here is that we can deduce gamma of S pi psi times gamma of 1 minus S pi check psi is equal to the central character of pi evaluated at -1 here. So omega pi is the central character of pi. Yeah, let me give a sketch for this corollary. The main ingredient is that if you apply the Fourier transform twice, then you just get f of minus x. Okay. So first, we apply the functional equation to the function S, F, double F, F here, phi, then you know that it's equal to gamma of 1 minus S pi check psi of Z 1 minus S FF and phi check. Yeah. Then you again, you apply the functional equation to this term here, then you simply get gamma of 1 minus s pi check pi and the gamma of s pi psi z of sf phi. On the other hand, since you know that if you apply the Fourier transform twice to the function, then you get f of minus x, so the left-hand side here becomes omega pi of minus 1 times z of sf phi. Then comparing the left-hand side and the right-hand side, you immediately get the functional equation. So, functional equation holds. Okay. So these are the main corollaries from the main theorem proved by Goodman and Gcd. Next, let's see the relation with the parabolic induction. Let's first show that if the theorem holds for any representation on the Levi factor, then it holds automatically for any subrepresentation of the induced representation. Okay, so let me see. By the work of Gcd and Hershchandler, we know that for any irreducible admissible smooth representation pi of G, you can always find some supercuspidal representation on the Levi factor such that pi embeds into the induced representation. So P is a parabolic subgroup of G with Levi decomposition m times n. And the tau is a supercuspidal representation of the Levi. If the Levi factor, if the Levi has a factor GL1, then it just means it's a quasi-character. Yeah, periodic. Yes, you're right. Yeah. Archimedean then is always a character by the theorem proved by Kessler. Okay, so in our setting, our group G is GLN, then we can pick up our P to be a standard parabolic subgroup. And for convenience, let's see the case when P is a maximal parabolic subgroup. The general case follows from the induction. Let's assume that P is a standard maximal parabolic subgroup. In G of type M1, M2. In other words, we assume that M1 plus M2 is equal to N. And P is of the following form. Here's GL M1, here's GL M2. Here's the unipotent radical. Then, in particular, the Levi factor is isomorphic to GLM1 cross GLM2. Then we can assume that tau is isomorphic to tau1 tensor type tau2 anyway. Here, tau I is a supercuspidal representation. or quasi-character if mi is equal to 1. Okay. Then let's first briefly recall the basic properties for the induced representation. So first, the vectors in the induced representation consist of smooth functions f from G to v tau. Here v tau is the underlying space of representation tau here. It is smooth such that f of p times g is equal to delta p half and tau p fg. Here the unipotent radical just acts trivially. The second fact is that if you take the smooth contragradient of the induced representation, then it's isomorphic to, you apply the induction to the induced representation to the smooth contragradient of tau here. And third fact is that if you pick up two vectors, f lies in the induced representation, and f tilde lies in the smooth contragradient duo, then if you want to compute the matrix coefficient associated to f and f tilde here, we let phi g to be f tilde induced gp tau then it can be computed in terms of the matrix coefficient of tau. So it's equal to k f tilde k and fkg. Here k is the fixed standard maximal open compact subgroup of G. Yeah, then we want to, our goal is to reduce the series of zeta integrals associated to pi to tau. To reduce. To zeta integrals for tau. Okay, then let's just run the definition. We let f to be a test function. We let phi to be a matrix coefficient of the induced representation. Not just the induced representation. Let's first fix matrix coefficient of pi anyway. Yeah, you find that the induced representation might be reducible, but you can still run the zeta integral procedure for the reducible representation here, just by definition. Since we know that pi embeds into the induced representation, then in particular, the matrix coefficient for pi lies in the matrix coefficient for the induced representation here. In particular, you can always pick up some vector f in the induced representation and f tilde in the smooth conjugate dual, and form the following matrix coefficient. Then let's run the theta integral, say as f phi, and write out the definition. Okay. Then we just use the explicit expression of the matrix coefficient here. So it's equal to integral on G cross K of Fg F tilde of K and Fkg dk, then determinant G of S plus n minus 1 over 2 dg. You just write out the definition for the matrix coefficient here. Okay, then let's do change of variable. We change G to K inverse G. Then the integral here becomes G times K of F of K inverse G. And here's F tilde K, and here's F of G. We take the pairing on tau anyway. Determinant G of S plus n minus 1 over 2 dg. And here we notice that if you take the valuation of the determinant of any matrix in the maximum open compact, then it's always 1. So here is still determinant of G. Then from the Iwasawa decomposition, we can deduce that G is equal to P times K. Then we can decompose the variable G here in terms of integration on P and K individually. Let's write G equals B times K here, or P times K here. Then integration becomes K cross K cross P, and the F of K inverse P K tilde. Yeah, here I should write G equals P times K tilde. Yeah. And here's delta P 1/2, and the F of tilde K. And here's tau P times Fk. You take the pairing on tau. And here's determinant of P to the S plus n minus 1 over 2 dp dk tilde. You use the definition of the induced representation, and you can further simplify the integration of the to make it to be of the following form. Then let's write P as G1, U, G2. Here Gi lies in GLMI, and the U is an element in the unipotent radical. Here, let me briefly mention that the Haar measure associated to P is equal to determinant of G1 to the M1 times determinant of G2 to the minus M2. This can be done by explicit calculation. So this is a fact. Moreover, let me show you an explicit expression for the Haar measure for P here. And dP is equal to 1 over determinant of G1 to the M2 dG1 times dG2 times du. Then the zeta integral here can be further simplified as follows. So it's integral on K cross M cross N of the following form: F of K inverse G1 U G2 K tilde, and the F tilde K tau M F K tilde. You take pairing on tau again. And here becomes determinant of M1 of S plus M1 minus 1 over 2, and determinant of M2 S plus M2 minus 1 over 2. In particular, we find that the zeta integral right now becomes very similar to the zeta integral associated to the Levi factors. What is needed to show here is that you need to show that this function lies in the Schwarz space of the Levi factor. Ah, yes, you're right. Thank you. Now here I should write it's G1, G2. So we find that this is a matrix coefficient for sigma 1 times sigma 2. So what is left to show is that the following function, so only to show the following fact, which describes the relation between the Fourier transform and the parabolic descent. The following lemma, if you fix a Schwarz function, then the following function in variable G1 and G2 lies in the corresponding Schwarz space on the Levi vectors. This lemma, let me give a brief sketch here. So this lemma directly flows from the fact that the original Schwarz space is isomorphic to a tensor product of n squared copies of CC infinity functions on F. Then you simply take the integration for the variables here. You immediately get that the function lies in the corresponding Schwarz space on the Levi factor. Okay. So in particular, for fixed K and K tilde, we know that the following function, if you take the unipotent radical integration, then this function lies in the corresponding Schwarz space on the Levi factor. Finally, you use the K finiteness of the original Schwarz function and the matrix coefficient there. We find that the original zeta integral here is a finite linear combinations of zeta integrals on the Levi factor. So the original zeta integral is a finite linear combination of the zeta integral of following from Zs Fi or F1 phi 1 times Z as F2 phi 2. Here Fi belongs to the Schwarz space of Mi, and phi is a matrix coefficient of sigma I. In particular, we find that if the Gcd property holds for sigma 1 tensor sigma 2, then it holds for any sub-representation pi inside the induced representation. Okay, so we find that we can reduce for instance, the Gcd property to the V factor. And here I would like to mention that the L factor for pi is not exactly the product of the L factor for sigma 1 and the sigma 2. Sometimes it is the product of the two factors, but sometimes not. So let me briefly make a remark here. In particular, we find that the L factor of sigma 1 times sigma 2 no. The L factor of pi over L factor of sigma 1 times sigma 2 lies in C of Q to the S, Q to the minus S. However, they are not always equal to each other. For instance, let me give you an example. In the case G equals GL2, we consider a Steinberg representation of G. Then we know the Steinberg representation embeds into the induced representation GL2. Here's the standard Borel, and here's the modular character of Borel. Then you can show that the L factor for the Steinberg representation is equal to 1 minus Q to the minus S minus 1/2 to the minus 1. It only contains one L factor, not always the product of the two. But in the GL1 case, it's a quasi-character. If the corresponding Levy factor is GL1, then it's a quasi-character. Yeah. And here, because the Levy factor is GL1 cross GL1, so it's just two characters. So any other questions? It's true. Because you just find that from the definition. If you run the procedure, then you find that actually the functions fulfill the whole space. And the matrix coefficient is always also the full space, actually. Yeah. So any other questions? Okay. Then we have already shown the Gcd property. What about the functional equation? If the functional equation holds for the representation on the Levy factor, then what about representation pi here? The function equation for the Levy factor also deduces the function equation for the induced representation. In order to prove the claim, let's show the following lemma, which describes the relation between the parabolic descent and the Fourier transform. Okay. lemma. Again, if we fix a test function, and the G1, Gi belong to M of Mi, here I equals 1 and 2. And we define Rf of G1, G2 just to be the parabolic descent we have already seen before. Then, if you first apply the parabolic descent, then take the Fourier transform, it's equal to, you first apply the Fourier transform, then take the parabolic descent. Yeah. Here, the left-hand side takes Fourier transform on the Schwarz space of the Levi vector. And the right-hand side takes Fourier transform on the original Schwarz space. Okay, let's try to prove the lemma here. Let me briefly give a sketch. So let's see the right-hand side. So by definition, it's R of F check. Evaluate at G1 and G2. By definition, you first take the, let's just run definition anyway. So it's integration on N of F check G1 U G2 du. Okay. Then, by the definition of the Fourier transform, you take integration on N, and here's Mn. And here's F of ABCD. You have 4 blocks, and the psi of trace of ABCD times G1 U G2. Du and dA dB, dC dd. Then if you compute the term here, you find that let's first take the product of 2 matrices. So it's AG1, and here's CU plus DG2, whatever. Then you take the trace. Then it's just a trace of AG1 plus CU plus DG2. Okay. Then in particular, you find that if you take the Fourier transform for the variable C and the U here, then you get the inversion formula. In other words, you apply the Fourier inversion for variable C and the U. Then you get it's actually equal to integration on variables A, B, and D of F of A, B, 0, D. And here's psi of trace AM1 plus DM2. dA, dB, dd. Which is exactly the left-hand side. So in particular, we have proved the lemma here. So the key point is to apply the Fourier inversion for these 2 variables anyway. So any questions? Okay. I think I should just stop here, and later we will talk about the functional equation part.